Good morning, students. So last class we saw the implementation of queues. We did the program on that, and we also came to a situation where there is a small problem with the implementation, with the array implementation of queues. Specifically, there comes a situation once we have done enough enqueue and dequeue operations on the queue that even when the queue is actually empty, we are unable to add any more elements because the condition becomes so that it says that the queue is full when actually it's not full, and we don't want to shift elements to the left every time we delete an element from the front of the queue. So this we have discussed in the last class. So today we'll try to work on that problem, and basically what we would like to do is, because we are using an array implementation and because we won't be shifting elements every time we delete an element from the front, what we are going to do as a solution for that problem is use of a circular queue. Okay, so as the name suggests, circular queue is a queue in circular shape. Okay, no surprise there. So let me just put an index here. 1, 2, 3, 4. Let's say the maximum number of elements is 5. Okay, so, and because we are still using an array implementation, we will go from 0 to 4. Now this is what a circular queue looks like, okay, as far as we are concerned. But in the memory, of course, we cannot have any circular structure. So this is what we call as the logical view. Okay, and the actual view looks like this. So this is 0, this is 1, this is 2, this is 3, and this is 4. Right? This is the normal array implementation of a queue. And by circular, what we mean is once we are at the end of uh, the queue. By end, what I mean is the last index, maximum index possible, because max queue is 5, so it will go up to 4. Once we reach the end of that index limit, we need to go back. Okay, and that is how we make it circular. I hope this is clear. So if I had to draw this arrow thing here, it will go something like this. So it's like 0, 1, 2, 3, 4, and 0, 1, 2, 3, 4, and so on. Okay, so this is the physical view that we will have on our computers in the memory, but logically this is what we have to remember. So basically, what is a circular queue? It's a queue only, it's a linear queue only, linear data structure. The only thing that we are trying to add here as an extra is once we reach the end of the queue, once we reach the limit of the index of the array that we are using, we need to go back to the starting index, that is 0. Okay, if we can come back to this, we make it circular. So that's all we need to remember. Now let us do some examples here itself. Let's say I have 5 numbers, or maybe 4 numbers. Let's try it out. Let's add 10. So where will 10 go? 10 will go to the first one, right? Oh, we need the pointers also. So initially let f front and rear point to -1. -1 being an index which does not exist. Okay, so initially f and r are pointing nowhere basically, but once we have added the first element, okay, what we will do is we will make both f and r point to that. I hope this is fine, right? This is the initialization, and this is like in an in an empty queue, when we add for the first time, when we insert an element for the first time, we initialize both f and r to 0. 0 means this index 0. Okay, so basically both are pointing to 10, the first element. Actually the only element in the queue. Okay, done. So it's like this. Okay, then we add 10, then 20, then 30. Okay, let's keep doing this. And every time we add, which pointer should we move? If you remember the queue definition, where do we add the elements? We always add it to the rear. Okay, so every time you add an element, you need to move the rear pointer. Every time you delete, you need to move the front pointer. Because now we are adding 3 elements, we have already added 10. Let's add the next one, 20. So where will R point to? R will point to this, basically to index 1. Okay, I hope that is clear. And so on. So next is 30. Let's add it here. What do we need to do with the rear pointer? We need to update it, right? Okay, let's do that. Basically just increment it, that's all. So it was pointing to 1, just increment it, make it point to 2. 2 means index number 2, so you are basically looking at 30. Okay, so this is how we are going to go. So here also, yeah, I can add it, but if you understand with this, that is actually enough. Okay, you can always try it out here. It doesn't really matter. Okay, but because we are working with a circular queue, it's better to visualize this as a circle instead of a normal array kind of thing and this arrow going back. This is the physical view that is actually going to happen in the memory. Okay, so I will stick to this. Fine. Let's dequeue or delete. Again, we cannot give an option which element to dequeue or delete because by default it's the first element of the queue. So if I dequeue it, what should I do? This is similar to what we did yesterday. Whenever you enqueue or whenever you add, you need to increment the rear pointer. Whenever you delete, you have to update the front pointer. By updation, what I mean is just increment it. Okay. So if I say dequeue, this 10 will go away. What will happen to? So we know that 10 actually, because it's an array thing, it never goes away, right? But the only thing that will happen is we will need to update this front pointer, right? And this is now basically pointing to 20. So if you were to run a loop to check all the elements of the queue, you will run the loop from F to R, so you get to see only 20 and 30. So 10 is like kind of out of the picture. So we can safely assume that it's deleted, okay? But because it's not a linked list implementation, it actually doesn't get deleted. So that is something I have discussed many times before. That's how we work with arrays. Okay, so yeah, let's add few more elements. Add 40, 50. Okay, let's add 40 and 50. So 40 gets added here. Let me add 50 also. It will happen one at a time, but just to save our time for this video lecture, I'll just do it once. And what happens to the pointer? Obviously, it was pointing at 2. Now it will be updated and it will be pointing at 4. 4 means index number 4. Okay. Let me just delete or erase this part because it's kind of deleted. No, then it's gone. Okay. Right. So what we are looking at right now is something like we are at the end. See, there is no end or starting point, okay? But because we know this is just a logical view, okay? So the index is going to end now. So this is like at the maximum possible index value, 4, right? Because max q is 5, it will go all, if max q is n, whatever, it will go up to n minus 1 because we are starting from 0. So n minus 1 will be 4. So we are already at the maximum permissible value of index number. Now, what we need to do now, let's try dequeuing. I'm just trying to explain how this circular queue is being used. Okay, let's dequeue. Um, dequeue, dequeue, and dequeue. Okay, let's delete 3 elements, 1, 2, 3. So this is gone, this is gone, this is gone. So basically the front pointer would now be pointing to, oops, okay, because 20, 30 and 40 are deleted, right? Now, see, this is the situation that we were in yesterday. So if you can recall back, I don't know where it is gone. So it's like we're somewhere over here, right? Or maybe I've erased that, or yeah, something happened here. We did a lot of discussion and somehow I ended up like this. So it's fine. So if we were to delete all these things, I'm going back to yesterday's discussion, okay, yesterday's implementation, right? So F and R are both pointing to this. So now if I say NQ, right, add 50, okay, what will happen? If you look at the code, I hope all of you have the code written in your notebooks. If you look at the code that we used yesterday, what is the code to check for overflow? If real is equal to or greater than next q minus 1. In our case, next q was 4, okay, because next q is basically how many elements you have in the queue. So next q minus 1 will be 3. So it's saying the condition, please look at the code that we wrote yesterday. If the rear pointer is equal to 3 or greater than 3, right now it's equal to 3, right? It means the queue is full, you should not be able to add any more elements, right? And we stop here. But you see, I've already deleted 10, 20 and 30. F is also pointing to 40 only. So we have actually 3 more spaces here, but we were unable to use this. Now this thing can be easily solved here. So we are exactly at the same situation. Front is pointing to 50, the only element left in the queue. R is also pointing to 50, the only element left in the queue. And index number is the maximum one, right? Okay. Now, just for the sake of absolute clarity, let me just delete all these things because these are already gone. Okay. So now, how do we add? Now we can see that there are a lot of empty spaces, right? So in a circular queue, the main advantage is this one. This is basically the solution to the problem we were discussing. So what we need to do is, if we are at the end of the queue, the linear thing. Okay, how do we know we are at the end? We can simply check the index number, right? It's max q minus 1. 5 minus 1 is 4. So we now know that we cannot just, like if I say add 60, okay, add 60. So we would, if we don't have circular queue, what we will try to do is we will try to implement, pre-increment or post-increment, whatever, pre-increment R. Now that will take us to 5. We don't have a 5 here. Okay, so this is a special case where we have to take care that we just don't increment all the time. If you reach the end of, the circular queue, not the end of the circular queue, but if you reach the end of the limit of the index number, 4 in this case, or next q minus 1, we simply need to reset this index number to 0. Okay, so now if we were asked to add another element in this situation, okay, all we need to do is, we cannot do plus plus r because that will take us to 5. We don't have a 5 index, right? That's the same problem as before. Now the solution in circular queue is very simple. If you have reached the end of the array, okay, because it's basically an array only, all you need to do is reset R to 0 and then add. So there is R is pointing to 4. So let me just remove this entire thing. And instead of this pointing to 5, which does not exist, we'll simply make it point to 0 and then we can add 60. So you see it has crossed the boundary and it's actually back to this one. So like here it was, let me just show you. So we were in this situation, okay, where 50 was the last element and front and rear we're pointing to this. If you compare this situation with the normal implementation, this one, it's exactly the same, okay? In the normal implementation that we did yesterday, we won't be allowed to add any more elements, even though there are a lot of empty spaces. But here, what we are going to do is, because we know that we have some space left and the array is not full, or rather the queue is not full, all we need to do is, we just need to go back, okay? It's called a wraparound. It's basically a modular thing, no? All of you know the modulus operation, right? What it does. It's just a modular thing. We just need to wrap around and go back to the beginning of the queue. So instead of R pointing to 4, what we did just now is we reset R to 0. So that basically takes me here. And this is the place where I can add 60. So, okay. So whether you understand it this way or this way is preferable, like I said, because we are working with a circular queue. But in any case, if you want to do a comparison between what we did yesterday and what we are doing today, this could be more helpful. But try to stick to the circular representation. Okay, so this is not everything. Like I have not really discussed how to check for emptiness and how to check for overflow and all those. We'll do those while we are writing the program. But I think what I have done till now is I have tried to make you understand what a circular queue is and how it actually works with NQ and DQ operations. Fine. And how it solves yesterday's problem. I think that's the most important thing we need to keep in mind. Okay, now let's quickly come up with the solution for overflow and underflow. Okay, let's stick to the same example. Let me just do underflow first. Like, how do you check for emptiness of a queue? So it's like, yeah, let me do it here. So let's do DQ and another DQ. Okay, so when I do DQ for the first time, this 50 is gone. And again, because we have reached the end of this thing, we cannot do a plus plus front, no? Every time you DQ, every time you delete, you have to update the front pointer. That is basically an increment operation, but because this is like we need to wrap around, so just like this NQ thing which we did here, reset R to 0, here we have to reset F to 0 because you cannot go to 5, there's no 5, there's no index number 5. So what we will do is we'll simply make it point to 0. Okay, and of course this 50 is gone. Okay, another DQ operation, let's do it. What we need to do now is remove this, right? And then, yeah, see, this is the only element left, right? This is the special case. This is the only element left in the queue. So if you delete this, F should not be going to 1. What is F? F is a pointer pointing to the beginning of a queue. Now, when I say queue, a queue needs to have elements, right? You cannot say there is a queue of 0 people standing outside the ATM machine. You know, it doesn't make sense. You need to have people, you need to have elements to make up a queue. or a stack or whatever, you need data. If we are deleting the only data left, it does not make sense for f or the front pointer to point to any of the index. Like in this case, if we just do a plus plus f, it will go to 1. 1 is really not the beginning of a queue because there is no queue. Once I delete this, f should be reset to -1. Okay, is this clear? So once I do this dequeue and I know that there is only one element left, this is a special case, so I will need to reset f to -1. So if I delete this, f becomes I'm writing it in the reverse order. I should not be doing that, right? It will confuse some of you. And it's not correct also. Let me just so f, which was pointing to this index number 0, will now be pointing to -1 because the only element that was there in the queue has been deleted. Okay, just keep this in mind. So coming back to the underflow condition, what is the condition to check for underflow? So only thing you need is if underflow is if check just check if f is equal to -1. If it's equal to -1, then it's an underflow. Matlab, it's an empty queue. Okay. Now, I will just retrace back my steps. If we had not deleted it yet, let me just. So I hope this condition is clear. Okay, just keep that in mind. We are done with that then. Now let's say we had 60 here. Okay, 60 is here, and f is still pointing to that. Now, how do I know that this is the only element left in the queue? Okay, so you see, whenever f and r are pointing to the same index, it could be any one, it need not be 0, it could be at 1 also. It depends on the sequence or order of DQ and NQ that you might have done. But if f and r are equal, meaning they are pointing to the same index, what does it mean? It means only one element left in the queue. Okay, and that we had seen in the earlier discussion also when f and r were pointing to 50, both were pointing to the same index number 4. And there we had only, that meant that there was only one element left in the queue. So these are some of the things that we have to keep in mind, okay? So initialization, beginning of the entire process, both f and r should be initialized to -1. How do we check that there is only one element left in the queue? That is, if f is equal to r, not assigned, okay? It's equal. Then we discussed how to check for underflow. This is like based on our discussion, what happens when we delete the only element left? F has nowhere to go, so we just reset it to -1, and that is what we take up as a condition for underflow. Okay. Yeah. So that is one thing. What else have we discussed? We'll do overflow just now after this. Just trying to think of any other thing that we might have missed out. How do we know that we have reached the end of the array and we need to do a wraparound? What would be the condition for that? So we just have to check. Depends on what operation you are doing. If it's an NQ operation, means insert operation, you are to look at the rear pointer. So you will check if rear is equal to max q minus 1, then it means you have to reset r to 0. This one. How do you know you have to do this? So it's basically this condition. If r is equal to max q minus 1. Similarly, if you were deleting, right? So you are basically moving the front pointer. And if you reach uh, an index which is actually max q minus 1, you need to be careful, you need to do a wrap around, you need to go back to 0. So same here, but instead of checking with r, you will need to check with f. So you will say if f is equal to max q, I'm just writing q, okay, max q minus 1, okay. So something like this. If f is equal to max q minus 1, or if r is equal to max q minus 1, depending on whether you are doing a NQ operation or a DQ operation. So some of the things that we are coming up with is this one. These things are going to be useful when we write the program. Okay, this is something we just discussed, and this one also. 1, 2, 3, 4, 5. Right. Now let's discuss the last one. How do we check for overflow? What is overflow? Overflow means, see, there will come a time, there can come a time, it's not like certain, but it depends on like situation where you are only adding elements and not deleting enough. What will happen is there will come a time when the queue is actually full. Okay, so whether it's a circular queue or not, it doesn't matter. The queue will get full unless you delete an element. So that is the overflow thing. How do we check for that? For that, we have to do a quick example. Okay, let's do that. So let me delete this. We are back with a circular queue. Let's add some elements. 10, 20. Front is here. This is like the beginning. This could be one situation. 40, 50. You see, now the queue is full. So what is the condition? This will help you, or this will rather help us think about what could be the condition that we need to write for overflow. So what is the situation right now? Front is at 0 and rear is at 4. Okay. Now 4 is a very specific number. So what we will need to write is, I'm just going to erase these things. Okay. So one possibility for overflow condition could be if f is equal to 0 and r is equal to what? 4 is what? Max q minus 1. Okay, so this, you see, it's actually full, right? So that's how I'm coming up with this solution. See, from exam point of view, or even when you're using these data structures in your programs in your own way. Okay, not everything is not exam, right? You need to use these in some applications in the future. So this is how you should come up with your own code, own conditions. Okay, you don't have to go back to Google or your textbooks all the time. Just try to come up with all possible scenarios, and your program should be okay. Everything is not there in Google. Of course, these things will be available because these are very standard topics. But if you were developing something on your own, obviously you cannot expect solutions on Google. So please have a habit of doing things yourself. So this is one condition or situation where the queue is full, and we have taken that into consideration. Let's DQ now. Okay. Okay. Let's DQ. Let's delete this one, this one. Okay. Let's delete twice. So where is f now? So if I delete this and this, f will be now pointing to 2. Okay. Is this clear? So let me just erase this. It's gone. And then let's add a few more elements. Let me add 60. So rear is here. Let me add 70. So where is rear now? Rear is pointing to 70, meaning which index number? Let me just remove R from here. Yeah. Okay. So you see the queue is full again, but this time the situation is a little bit different. So this condition 1 will not really take care of this. So this is one very specific situation, and this is something that can happen anywhere in between the inside the queue. So what is the condition here? Just look at the figure and try to come up with the code. If queue front, okay, is, where is queue front? What is the index number? 2. And what is the index number of the rear pointer? 1. Okay, so basically the condition is if front is equal to, front means this index number 2 is equal to rear plus 1, then also it means that the queue is full. Okay, so it's another overflow thing. Right, apart from this, there's nothing else that, there's nothing else we need. Okay, so we have done for underflow check, which was quite simple. Just check for -1 if front is pointing to -1 or not. Overflow is involves a little bit of things. It's not as simple as or straightforward as the underflow check, but again it's quite simple. So you just need to come up or remember these situations. So this is the first one and this is the second one. Now this second one can happen anywhere inside the queue. This first one is quite special in the sense that only when front is pointing to the first element, and the rear is at the end of the array, because it's basically an array only. So that's when you have to use this situation, sorry, the condition. So if we add or if we combine both these, we should have a overflow check condition. So we have all these things in place. Please note it down, pause the video now. Okay, just write these conditions in your paper somewhere. Init, underflow, overflow, checking for only one element left in the queue, how to do how to know that you have reached the end of the limit of the index number. When you are doing an NQ operation, this would be the condition. When you are doing a DQ operation, this would be the condition. Okay, just keep these things in mind, and with this, we are kind of done with the the discussion about circular queue. I think it's time to go to the code, right? Okay. So you can pause the video, you can rewind it, make sure you have understood everything up to this point, and then we should be good to go with the next discussion. Okay, I'm going for a new page. Before I write the code, I feel I should explain the operations first. Let us write it down so that it's easier for us to program. Okay, so let's write down whatever we have discussed till now. Initially, front and rear both are assigned -1. Okay. Let's talk about the insert operation or NQ operation first. So whenever we try to add something to a queue, we need to check for overflow. Now that we have already done. So the first thing we need to do is check for overflow. I'm not going to repeat the code here. Okay. This is the thing. Fine. So assuming you guys have written this down in your notes, you should be able to refer it anytime you want. So we check for overflow, that's the first thing we need to do. And only if there is a space in the queue, only then we go for the NQ operation. Okay. Now there are three cases. Because it's a circular queue, there are specific cases which you might have understood already. Like when you are adding, like this is one special case, right? When you reach the end and you have to do a wrap around and so on. So let's discuss them one by one. So case one is empty queue. So what is empty queue? Empty queue can come up when this is like the first time we are adding an element into a queue, or it could be like all the previous elements have been deleted, right? And we are basically starting afresh with the insert operation. So case one could be empty queue. What if the queue is empty? Now how do we check for that? How do we know that a queue is empty? You can simply use this thing, okay? But here you should not be using assignment. You should be doing a check. That is, if front is equal to r, which is equal to -1, okay, then I hope all of you remember when we added for the first time, what we did with f and r was we set both of them to 0, right? Okay. If you followed the lecture properly, you'll remember that when we added for the first time, the first element, we made both f and r point to the first element 0. So that is what we need to do. Set both f and r to 0. Okay? That is, f is assigned 0 and r is also assigned 0. Now once we are done with the pointers, we still have to do the operation, right? So after you have updated the pointer, add the element at the 0th position. Now what exactly is 0th position? Rth position. Now this r is obviously 0 because there's a special case, the first element to be added. So add the element at the rth position. Simply use r as an index in an array representation. That's it. So this is case 1. Case 2 is what we discussed before. If you reach the end of an array, or the queue rather, you need to do a wrap around, right? So you see, you remember this one? So we'll be using that. If r is equal to next queue -1. See, to really understand all these things, you have to understand everything, or we discussed up to this slide, okay, on this page. So then it's very easy to understand all this. So if r is at the end of the array and we need to make it circular, we need to go back. Okay. So what we need to do is, reset r to 0. That is, r is assigned 0. Because we cannot do a plus plus r, it doesn't make sense. Okay. And once we have taken care of the rear pointer, that's where we are going to add the element at the rth position. So this is like a common thing, right? So the first thing we need to do, whether it's case 1, case 2, or whatever case we might be in, you always need to update the rear pointer first if you are doing an insert or NQ operation. And then once you are done with the updation of the rear pointer, then only you add the element. What would be case 3? Case 3 is like all special cases taken care of. So basically it's like you are adding an element somewhere in between, right? Okay. So in that case, you just have to increment the point. That's it. Just increment r. It's not really a code. Let me just remove this. Increment r, and then add element at the rf position. So this is like for all other situations other than case 1 and case 2. This will be like anywhere inside the cube. Okay. So this is like an empty cube, special case. This is like at the boundary, and this is anywhere inside the cube. So most of the times you will be here in case 3. You will be just incrementing r. So this one you should be able to understand really well, because this is what we do anyways, whether it's a circular cube or a normal cube. Okay. So with this done, insert operation is done. Let's go for the DQ operation. Delete. So the first thing is we need to check for underflow. Now how do we do this? We have already discussed that. We just check if f is equal to minus 1. Okay, that's it. So once we are done with that, and we know that the queue has some elements which we can delete, we start with the first case. Now what is the first case? First case is what we had discussed earlier. If there is only one element remaining in the queue, okay, and if you delete that, what should you do with the front pointer? We already know it, right? If you remember 60, if you have only one element left, and f and r both are pointing to that, okay, which is basically this condition, you need to reset f to -1, and you should reset r also to -1. Okay, so that the check for what is this? Yeah, the check for empty queue becomes true. Like next time we try to add something, okay, that should fall into case 1. Okay. So case 1 in case of delete is if f is equal to r, that is only one element left in the queue. Okay. What do? We simply reset f to -1. Also r to -1. I'm putting this in bracket because see, when we deal with delete operations, no, it's only the front pointer that is important. But because it's a special case, if I don't do this r, if I don't reset this r also to -1, see what will happen once you delete the only element left in the queue. The queue is actually empty, right? And we already have a condition for empty queue. That is, both f and r should be equal to -1. To come up to this condition, to make it true, which is the situation right now, because the only element in the queue has been deleted, so this is simply not enough only to reset f to -1. We should also reset r to -1. Okay, I hope all of you get that. Okay, one thing I'd like to tell is, before we delete, okay, this is not really a mandatory step, but we can store the element, the current front element of the queue, okay, in a temporary variable. Now this is for situations when once you have deleted front element, you would like to use that front element somewhere. So, just think of any real life scenarios like where you have the elements are actually processes. Okay, so P10 process number 10 is at the front of the queue. So just deleting it or removing it from the queue might not be good enough. You know, that P10 or process number 10 has to be given to the processor. So to keep a track of which process actually gets the processor, which has been deleted or removed from the queue just now, it would be a good idea to store that in some temporary location. Okay. So that is what we will be doing it for every delete operation. So case 1 is done. Case 2, what if yeah, case 2 is this one. While deleting, we see that we have reached the end of the queue. Okay. By end, what I mean is end of the array. Because it's a circular queue, we need to do a wraparound. So that's a special case, similar to this case number 2 of your insert operation. Here we were checking, comparing r's value with next q minus 1. In case of delete, we will have to check if f is equal to next q minus 1. Okay, if that's the case, we need to do a wraparound, reset f to 0. Wraparound, okay? I hope this is clear for everyone. If you were deleting this one, this 50, you once you delete it, you cannot go to 5. There is no 5. You need to go back. Okay, this is called as wraparound. So f which was pointing to 4 should be reset to 0. So it's a special case, right? It will happen only when you reach the boundary. Case number 3 is everything else in between. Okay, inside the queue. So there you just need to implement the front pointer. That's it. Just implement front pointer. That's all. Nothing else to do. Okay, this is a delete operation, no? So we are kind of done with all possible scenarios as far as insert and delete operations are concerned. We have written or we have discussed um, the logic and even the code, pseudocode to check for underflow, uh, to check for the boundary conditions, to check for overflow and things like that. We have kind of done everything. So now it's time to go to the program. So the program is something that I've already written. Okay. So before we go to the program, make sure all of you have written this down in your notebooks. Take your time. This is not a live class. So there are some advantages and some disadvantages. Disadvantage, the most important that I can think of is you cannot ask questions. Okay, you might be having some queries in your minds. I'm trying my best to explain it in the most, I don't know, most easiest way or complete way to make sure I don't leave anything unexplained. But then again, you might have some questions coming up, and that's why we will have live classes, live sessions before this week ends. But before that, you have to understand all these discussions, okay? So that's I think, the most important disadvantage of having recorded classes, lectures. Advantages, you can pause it, okay? You can pause the video, you can rewind it, you can skip some of the parts, you can do whatever you want, make sure you get it at your own pace. You don't have to be be in the same pace as me, because see, we have time constraint. Even in real class settings, we get maximum of 1 hour. Okay, so sometimes we tend to speed up a little bit. So that thing is not here in online recorded classes. So you have to take full advantage of that. Other than that, I think the other advantage is you don't have to wake up in the scheduled time, which is not something good. You should wake up early, but then again, if you are not an early riser, and if it's an 8 o'clock class, not a problem, you can watch these videos at night also. ठीक है Okay, so there are advantages and disadvantages. I think overall it's a good way of doing online teaching, okay, because we'll have live classes also. So make sure you have written this down, okay, this one, understood and written it down, and even the DQ thing. With that done, you should be able to understand the program very easily. Okay, let me take you to the code. Just checking if it's recording or not, right? So I hope this will be visible in the recording. I circular Q dot C. Okay. Okay, let's go one line, one line at a time. So we are including the headers. We have defined true and false. We have a mixed queue size of 5. This is just for discussion. Okay, you can make it go to any size. Doesn't it's not a problem. There's no restriction there. This is something we have already discussed yesterday, right? Because we are using an array to represent the queue. We have an array inside, and we also need front and rear pointers. So we have put them, all of them together inside a structure. Okay, and we have renamed the whole structure as queue. Insert, display, delete, empty, already done yesterday. Already done means the signatures I have already explained. Let's go to the insert first. Okay, please keep looking at the notes. Okay. So what is the check for overflow, insert. Okay, this code doesn't look right. Do I have another code? Okay, sorry about that. So the front part is same. Okay. Let's go to the insert function. So please look at your notes. What was the first thing? I put an asterisk marks over there. Check for overflow, right? So we already know how to do that. If front is equal to 0 and rear is equal to max q minus 1, or front is equal to rear plus 1, okay, we say it's an overflow and we come out of the code. You can put a return also instead of an exit. If there is no overflow, we go to case number 1. Please keep looking at your notes and the code, okay? That's how you will understand it very fast. What did we write in the notes? In case 1, if it's an empty queue, the first thing we do is we set both F and R to 0. How do we know it's an empty queue? Here I'm just checking for front, okay? You can check for both front and rear. It's not a problem, okay? Because if front is minus 1, obviously rear is also minus 1. But if you really want to make it same as the note that we have, or rather the discussion that we had just now, let me just do this. If q front is equal to q rear is equal to minus 1, okay, then what we do is we reset front to 0 and rear also to 0. Okay, you have to do it separately, or you can do it in one line also, but you know, separating out things like this makes it more clear. So this is case 1. Insert operation we'll do at the end. Okay. Case number 2, what is the thing? It's like the boundary condition, right? So if R is equal to max q minus 1, what did we do? We need to do a wraparound. Okay, so we do a wraparound here. Fine, we have done that. Otherwise, this is case 3. Case 3 may we just need to increment the rear point. Done? And once we are done with this, because it will be either of the cases, right? Not all of them. It would be like either of one of these cases. Once we are done with that one, once we have updated the value of rear pointer correctly, we simply need to use that as an index in the array items and assign whatever has been passed here. Okay. This is item, okay, this is items, this is the array. You can actually change this name to element or data or something like that. It's too close, okay, item and items. Fine, I'm not going to do that now because that will eat up more time, but I would suggest all of you to just change this item to something like LE. Okay, let me just do it here. Because items, no, some of you might be getting confused with that. Items is the array. LE is what we are trying to add. Okay. So done with the insert operation. Let's go for the delete operation. Let's go one by one. What is this? Empty queue. Check for emptiness of the queue. Simple. We just check if front is equal to -1. If it's so, return true, else return false. Okay. Where do we use empty? In delete and in display. The next function is your delete. So if you look at your notes, the first is we need to check for emptiness. So we call the empty function. If it returns true, we say there are no elements or underflow error, and we come out of the function. Otherwise, we continue. So in the else part, we have the three cases. Look at your node now for delete or dequeue operation. What is the first thing we need to do? We need to store the current element in a temporary variable. So I have already, again, see, the name is, I don't know why I chose the same, very similar name. So I can just say LE here. Okay, which means I have to change this also to LE. So this is the temporary variable where I am storing whatever front is pointing to. Okay, so using front as an index in this array items, I can get access to that element. I am putting that inside, storing that inside LE. Let me just return. Okay. I'm just changing the name from item to LE. Okay. So once we are done with that, let's go to the first case in delete. What is case 1? Case 1 is when you have only one element left. So this is case 1. How do we check? If front is equal to rear, if only one element left in the queue. This is case 1, no? So what we do is we initialize both front and rear to -1. Done? Otherwise, we go to case number 2. What is case number 2? It's the boundary thing. We need to do a wraparound. So by now, I hope all of you are able to understand this. So we check if q front, or front basically, the front pointer, is equal to max q -1 if it's sitting at the boundary. Okay, if that's the case, we simply say let's set front to 0 because there is no 5. We cannot do a plus plus front, a plus plus f. Okay, so this is case number 2. And finally, we have case number 3, which is like just increment the front pointer. So it's whenever you are inside the queue, not at the boundary, or not the special case number 1, then this is the thing that you have, that you will be doing, just increment the front pointer. That's it. Return element, like I told you, somebody might be needing the element that you just deleted, so just return it. Okay, so we're done with NQ and DQ, insert and delete operation. Empty is also done. Now we will be going for display. Now display is actually should have been very simple, but we just cannot go from front to rear, okay, because we are doing a wraparound. So for the wraparound, the code is actually very simple. We first check if the queue is empty or not. If it's not empty, only then we do this. So we have a loop starting from front, okay. It goes on until q is not equal to whatever, the I is not equal to rear. And for the increment thing, we are doing an increment, okay, but at the same time we are doing a modulo operation, because otherwise you will go beyond that thing. right, beyond 4. You'll go to 5, 6, like that, which, if max Q size is 5, the maximum index number would be 4. So if you just keep on incrementing, right, then it will not work, obviously, because you need to do a wraparound. So to do a wraparound, we just have to use the modulo operation, which basically gives you the remainder. So what I would suggest is, all of you, once you have a queue, circular queue populated, just run this loop, okay, yourself on paper. Just see how this particular line, how it works. Okay, I can explain it, but it's actually too simple. Fine. So you do that and you will understand it very nicely. So this is required for the wrapping around thing. And inside the loop, we just say, we just print out the elements. That's all. And when you do this, if you run this yourself, not on computer, but on paper, you will see that the last element is actually left out. Okay, that is coming out because of this condition here. So that for that last element that we could not print inside the loop, but which is actually a part of the queue, we will have to write a separate printf statement. Okay, that's it. So the display function is not so straightforward anymore, but it's again very simple to understand. So please make sure all of you run this code on paper, okay? Because a computer will anyway run it nicely. To really understand what is happening, why one element is being left out, which is actually very easy to understand if once you run this. You will understand this function. There's nothing very complex here. So with that done, we just need to write the main, which I've already done here. Let me just put correct return type and a return 0 here. And I'm just doing enqueue thrice, 1, 2, 4 times, sorry, 10, 20, 30, 40, and displaying it. Then I delete. So I'm basically deleting 10, 20, 30. 40 should be remaining when I display it. And then I add 50, 60, okay, and so on. So you can try this out on your own. This is just a sample. Please don't forget to do this in the main. This is the initialization part. Let me just take you back to that. This one. Init f is assigned, r is assigned -1. So in the code, this is where we are doing this. So please do not forget this, okay? Otherwise, everything will stop working. So let me just quickly run this program. Okay. Yeah, maybe that's the reason I deleted that. So line number 43. So instead of, yeah, we cannot really do this. Okay, this absolutely not correct. So I can actually do this and put this and here. So you cannot continuously compare, okay? It doesn't work that way. So you can say q front is equal to 1 and q rear is equal to -1, then this. Or you can just simply use this one and leave this one out, because in either case it will be true. Okay. So the error is, it was not really an error, but it's not good. Warning is also not good. So let me compile it one more time. No issues. Let me run it. So 10, 20, 30, 40 deleted items are, should have been R. 10, 20, 30. Item 3 contains 40. Now when we are adding 50 and 60, you see there is a wrap around here. I actually printed out with the index number just to show you that it's actually doing the wrap around, okay? So from 4, because max Q was 5, maximum index number would be 5 minus 1, 4. So the next element to be added will go to index number 0. But if you just remove this item 0, items 1 thing from the display, you will not even realize that it's actually doing a wrap around. Okay? So this is a very good solution using circular queue to solve the problem that we discussed in the previous class. So now with this, we come to the end of the discussion on Q. Now there are a lot of applications that uses Q. I've already explained that in the class. Now what I'd like all of you to do yourself, try out yourself, is try to implement a normal queue, not a circular queue, the normal queue that we discussed yesterday in the previous class, using a linked list. Okay, try not to look for codes on Google. So I will put that as an assignment in MS Teams. I'll set a deadline for that, but before that, make sure these two lectures are very clear to all of you, so that you can have some questions, some actually good questions when we come live next. Okay, so with this we come to the end of the linear data structure. From the next class I will start with trees, which will be the first of nonlinear data structure. Okay, then have a good day. I'll see you in the next class. Bye, take care.